Ignition sequence start. 3, 2, 1.
Houston, we have a problem.
Liftoff. We have a liftoff.
We copy you on the ground. You got a bunch of guys about to turn blue.
What you're seeing here is a mirage.
Are you ready? Debate fans, are you ready? For the handful in attendance and the thousands watching across the world, brought to you tonight by Jeranism, the #1 YouTube channel in all of existence. Ladies and gentlemen, let's get ready to rumble!
Make sure your argument is tight. Wait, what? You must got proof if you so right. Wait, what? Don't get dismissed on false claims, cause you gotta bring the truths and the facts. It don't matter if you're talking about racism, sexism, scientism, paganism, socialism, communism. Talk about capitalism, atheism, globalism. What about creationism? It don't matter what the ism. Live on Debatism.
And welcome everybody to Debatism. It's another fun episode we've got for you planned. A quick one, 90 minutes. We're going to try and get out of here if we can do so. Let me show you the thumbnail for the evening. We've got episode number 15, Angel Z versus Roohif on the shape of the plane or planet, flat versus sphere. All right, so that is the plan. And we should also be debating whether or not today is Tuesday or whether it's Wednesday. I think that's another debate we should be having because these two guys will both tell us that it's the wrong day. They think they live in the future somehow. But we know that's ridiculous. Let's bring them on. We've got Angel Z here on the left, and we've got Roohif on the right. And we'll let them say hello. Angel, go first. Tell us who you are, where you're from, why you're here, and I'll go fix the lighting in my... I guess it's fine. It'll work. Go ahead.
Yeah, my name's Angel Z. I live in Australia, and I'm about a little over a year into my journey into flat Earth. So 2 years ago, I was a globehead. Yeah, it's been pretty amazing, pretty eye-opening, and I don't think I'm ever going back. Yeah, that's about it for me. I'm here to prove that things can disappear over a flat plane just like they would disappear over a globe.
Okay, we're happy you're here.
Yeah.
Thank you very much for joining us. And then we've got Roohif. You've seen him before. I think he's been here on one episode or two.
Yep.
One.
I was in episode 6 of Debatism.
There you go.
I've been doing this for, I don't know, 6-7 years, something like that.
All right, well, welcome to the
it's
show.
fun.
Happy you're here. We will let Angel call the coin toss, and he can choose which he wants to go first or second. So I'm going to let the flip happen here. Up, that's going to work. There we go. Now we should see it. All right. So go ahead and call it heads or tails.
Heads.
Heads. So let's see, the flip is. And it is heads it is. So you get to choose. Go ahead and decide what you want to do.
So I can ask my question first, is that right?
Well,
Intros.
Intros first. So whether you want to go first or
right.
second, it only depends. You know, if you go first, you kind of set the stage. If you go second, then you get to end the show, being the last.
Okay. I'll go first. I'll just share my screen and play the video.
Sure. And we're going to give him 10 minutes on the clock on this one. He's got 10 minutes for his intro. Let me get that up there. And yeah, you're going to share your screen for the intro?
Yeah.
Okay. We've got
it's got
10.
sound as well, so yeah.
Did you hit share with sound?
Yeah, I believe so.
You hit the little check marks? Maybe stop sharing. Just make sure. Just go. Let me go stop sharing. Hit share screen again, and just make sure when you click it, there should be a little button in the lower left.
Oh, yeah. Okay. I see it. Yeah.
Gotcha.
All right. Cool.
Now you're good?
I'll just let that play.
Here's a simple demonstration showing how perspective works over a flat surface and how you can make objects disappear bottom up. And the same thing goes for boats. You can zoom back in on them over the horizon. They reappear and then disappear bottom up as you zoom out. Here's a sunset that is zoomed in on, and the sun appears to re-rise as you zoom in because the sunset's due to perspective, because it's moving further away from you. Here's a coin over a table. I zoom back in on the coin. I zoom back out on the coin. And then I sync that with the sunset to demonstrate the sunset's due to perspective. As you can see here, the coin disappears bottom up as well, just like that sunset in the previous video. All perspective. Sky ramps down, the ground ramps up. Just like streetlights, same with the sunset. They just merge into the vanishing point. Here's a man demonstrating that if you face north in the south, this guy is from Brisbane, he was facing north, and the star trails actually rotate counterclockwise again, just like they would in the north. If stars did move in different directions in the south, then it'd be pretty hard to circumnavigate using them. It would be really confusing using a compass because left and right would be opposite directions. This is the Eratosthenes experiment debunked. If you have a small local sun, the crepuscular rays would create shadows on an angle. And Neil deGrasse Tyson seems to think that we observe only parallel rays, which we don't. And he also doesn't think that adding an extra well will work on a flat Earth for some reason, even though it works perfectly. As you'll see shortly, having a local light source over a flat surface can account for all three shadows. Math doesn't change reality. This table is still a flat table. It's not a sphere. This is a video of clouds behind the sun, proving the sun is local. I put a negative filter on, and you can clearly see that the sun is nestled in the clouds there. And the same thing goes for the moon. There it is again, the sun, nestled in the clouds. And again, with the moon. Clouds in front and behind the moon. And again, clouds in front and behind the sun. Here's the Salanelian eclipse. This doesn't work on a globe because refraction only works with light and not with the shadows, so why do we still see an eclipsing moon? Here are my questions. Gas pressure. You can't have gas pressure without a container. It's in the definition of gas pressure. You can't have a vacuum without a container, and you certainly can't have them coexisting next to each other without a solid barrier between them. As you can see here, if the Earth rotates once every 24 hours, 6 months later, night and day should flip, because now it's still done the same amount of rotation, but now the country's facing the sun. 6 months later, now we'll be facing away from the sun. So I'd like an explanation for that. Also, according to the globe model, the Earth is on an elliptical orbit. So when it's winter in the north, the sun is actually closer to the Earth. So I don't know how that works. How do you get closer to a heat source and get colder? This is a passenger plane compared to the Felix jump, the Red Bull jump. And you can see from inside the cabin, they didn't have a distorted lens, and you can see that the horizon's perfectly level. And also the horizon in reality is an optical location that changes due to weather and other atmospheric conditions. If it's geometric, then technically you should be looking way down at the globe to see the horizon, but it always rises to eye level. Every terrestrial experiment to prove the Earth is in motion has failed. The only way you believe that it's in motion is by NASA or other space agencies telling you or showing you that the Earth is in motion with cartoons. Yet every experiment that has been done by scientists like Michelson-Morley, for example, to test that the Earth was in motion has failed. Yet Neil deGrasse Tyson wants you to believe that someone can kick a ball and the Earth can rotate underneath the ball and cause it to go into the goalposts.
Serenaded as he comes onto the field. Not bad when you're a kicker and there's new.
Other football tweet.
What other
about
football
was
tweet?
it the Bengals? I forgot who it was about a year ago.
Yeah.
There's in overtime, after there was the exchange of ball, so now it's sudden death overtime. They kick a field goal from 50 yards, of course, as it must be, and 40 yards out plus the 10 plus the hike and distance. So it was like 52-yard field goal, and there it was. And if there's tense, right? Everybody's silent, and the ball comes up, and it careens off the left upright and goes in for the win.
Wow.
And I said,
I remember this.
That's what I'm saying.
I remember this
That's
tweet.
what I'm saying. So I'm there and I'm saying, wait, the angle of this, how long is it in? So I checked the stadium on its configuration, what's longitude and latitude, and I said, I did a quick calculation, and I tweeted, the winning field goal in that game was aided by a 1/3 of an inch deflection to the right from Earth's rotation.
The Earth rotates once every 23 hours, 56 minutes and 4.09053 seconds, called the sidereal period, and its circumference is roughly 40,075 kilometers. Thus, the surface of the Earth at the equator moves at a speed of 460 meters per second, or roughly 1,000 miles per hour. The fastest Boeing 747 aided by jet stream is 825 miles per hour, so a Boeing 747 flying in the same direction as the Earth rotates at the equator would be going backwards according to the Coriolis effect.
Alright, I'm going to show you. The moon is see-through. See these images I got? This is one I took yesterday of the moon. And it's a raw file. See? Nikon RAW. Nikon RAW. This one, same thing. Nikon RAW. Nikon RAW. No compression artifacts. Okay? Now, I'm going to adjust the exposure up on the moon. Where is the rest of the moon? Like, it's a physical object, right? Where's the rest of it? Alright, look at this. Physical ball in a pitch black room with the light over it. Adjust the exposure up. You can see the physical ball. So, there is no way the moon is solid. Celestial navigation on a globe has actually just hijacked perspective and called it Earth curvature. They depict you in the middle of the globe looking up at the celestial bodies. In reality, you're on a flat plane and you see in a dome of vision, because that's how our eyes work. We see in a curved space. So things that are further away appear to dip down into the horizon, like I showed earlier, and a star that's further away from you will dip into the horizon due to perspective, not because it's a globe. All stars in the night sky relative to each other are fixed. They rise and set east to west, just like the sun. I fail to see how we have constellations still if the stars are expanding away from us at 4 times the speed of light, which is the claim of the globe, which is just ridiculous. How do we even have Polaris still in the same spot? It hasn't deviated an inch in all of history. So on a globe that is spinning, orbiting, wobbling, I just don't see how Polaris stays in the same spot all year round. It's not possible.
Yep, and that's it.
Okay, thank you very much for that.
Right,
We've
yeah.
got, next, Roohif. Are you going to be doing sharing your screen at all for the intro?
Probably not for the intro, because there are quite a few things in there that's new, shall we say, as in like not in the questions and claims.
Correct.
Yeah, it's just a generic video.
Yeah. Let's start with the.
So I'm going to give you a 3-minute clock. You go from there. If you need longer, let me know, because I know we gave him 10. But
we could probably do this after the questions. Actually,
do the intro after the questions.
Oh no! My intro's
Your intro.
30 seconds.
Okay, well, go ahead and do that.
All right. So my intro is basically I'm going to do geometry. Flat earthers have no idea about geometry. They basically think this is a conspiracy theory. It's not. Geometry. The word geometry, geometry, earth measure. Flat earthers don't measure the earth, and if they did, they would see it's a globe. I will address a couple of the things. So the camera looking across the flat bench top that you had set up, right? I assume that's a P900 or a P1000? Yeah? Yep, cool. What I've seen with those, Mitchell from Australia also did one of those. What he actually did was set up the camera very, very slightly below the level of the bench top. Then when he zooms in, what happens when you zoom in on a P1000? The lens extends, right? So if he's slightly below the level of the tabletop and he zooms in, the lens extends and is now above the tabletop. That's why you can see it. It's fairly, you can laugh, but it's quite dishonest of Mitchell from Australia. It's been replicated properly to show the effect. What else? The boats going over the horizon. You seem to suggest that the hidden amount actually changed as you zoomed in, but I didn't see any measurements of that. I can show you plenty of observations where the hidden amount does not change when you zoom in. It demonstrably doesn't. So that's that one. The moon one I found quite funny, where you said you changed the exposure, right? You didn't change the exposure. You changed the brightness and contrast of the photo. Okay. The exposure is a camera setting. Okay. So it lets more light come in. So when you're taking the photo and you change the exposure, looking at the crescent moon, you're letting more light in, right? So you'll see the half of the moon that's lit up, that will be overexposed and blowing out the sensor. But the dark part of the moon in shadow, you will then see as a solid object. All right. So that was a little bit amusing. What else did I write down? The star rotation. Yes, we look north and we see them rotate anti-clockwise. And again, we look south and they rotate clockwise. That is expected of a globe. That is the problem that we are telling you about, is the rotation. Yeah, you can unmute and respond if you want. So, I think that was all I wrote down.
On a flat Earth. So
I would love to see that model. Yeah.
Yeah, we can demonstrate it using a dome, right? You flip the dome upside down, you draw star trails, and then you move the dome to the south, right? And the star trails flip. And they go
from the inside? I have yet to see that model.
Yeah, I could probably show you a video of it, someone doing it, demonstrating it.
Okay, cool. That's my intro then.
Okay, we'll get into the questions, and just so people get it a little bit, because I did get some flack, I don't know if it was last week or the week before, but people are wondering, what's the clock for if Jaren's going to let the clock go over. The point of the clock is to kind of keep us in line, but it's also, if they're having a good conversation, I'm going to let it go. So I'm not going to interrupt a good back and forth because of the clock. The clock's just meant to be a guide, so I will manage the clock. There you go. And if you guys are interested in debating, you can do so. Go to t.me/debatism on Telegram. Put your name in the hat there. That's what basically happened with Angel. Is that correct? Is that where you guys met?
Debatism, yeah.
Okay. Yeah, so there you go. See? And then you can find somebody there to debate. And you can also email us at debatism@outlook and let us know if you're interested in what you're looking to debate, and we'll find somebody for you. All right, let's go to questions, and you're going to go first. Angel. And basically, you have a minute to ask, and he's got a minute to answer, and then we'll see if there's any back and forth needed.
Yeah. The question is, can you demonstrate one example of a pressure gradient next to a vacuum that's not the Earth, what's containing our atmosphere? If you claim it's gravity, please prove gravity. Prove it's it's what causes objects to fall and float with the current gravity model.
May I share my screen?
You may.
All right, so there are actually a few separate issues in there. Should I start with this one? I'll start with the other one, actually. Hold on, give me a sec. There we go. So you said, show me an example of gas pressure without a container, but I'm not allowed to show you the Earth. All right?
Yeah.
So I can show you, logically, one of two things. I can show you a container, or I can show you not a container. Okay? So on that circle on the left there, I've got a bunch of containers that I could show you that I can pressurize or make a vacuum or whatever. On the right, I have a list of non-containers. I can only think of one thing to put in that circle, and you've banned me from using it. Can you think of something else that I could logically, possibly logically use as an example?
Because it's impossible. That's right.
It's a logically incomplete question.
No, because you're assuming you're using the object in question and saying, "Oh, look, the Earth does it, right?" But I can demonstrate a pressure gradient with a container, right?
Yep.
And then I can go outside and say, "Look, a pressure gradient. It's contained as well."
Yeah. But the way you phrase your question,
but I can demonstrate
it logically impossible to answer. Logically impossible.
Because it is impossible to answer. The Earth is contained.
No. Not physically in reality, impossible to have an answer. But the way you phrase the question, if you can't literally give me a non-container, that's the only thing in my list. Right?
Right.
And you said I can't use it. So there's literally no possible answer.
But the Earth is contained. It's got a pressure gradient.
I agree it has a pressure gradient. I don't see why that leads to being contained. There is no container.
What's creating the pressure gradient?
The downward acceleration of the gas.
What downward? Explain that using gravity.
Yeah, gravity accelerates things downwards.
What's the current model for gravity?
Oh, you can either use Newtonian or Einsteinian.
No. You can't use Newtonian.
Why not?
The current model of gravity is Einsteinian gravity, bending space-time.
Okay, but I can use Newtonian.
No, you can't.
Yes, I can. I can throw a ball and model it with Newtonian kinematics. Yeah.
But you realize that your whole religion relies on Einstein being right, yeah?
No. I don't have to use Einsteinian gravity. I don't fully understand Einsteinian gravity. I just use Newtonian because it works.
What causes a helium balloon to float?
Yeah, it's less dense than the medium of tin.
So density and buoyancy, not gravity, right?
Okay, what's the formula for buoyancy?
Yeah,
how do you calculate?
Yeah, little g equals acceleration can be replaced with A.
Yeah, sure.
It's got nothing to do with gravity.
Right, there's an acceleration downwards, which is what I said.
Yeah.
The pressure gradient is caused by the acceleration downwards.
No, it's caused by electrostatics.
Okay, we can get to that shortly.
Let's go with Roohif, your first question. Go ahead.
Oh, have we finished this one?
Oh,
I had a few things to say.
Okay, go ahead. I'll give you another minute, but
well, you can.
Angel, mute just during his response to that.
Oh, he can read this off if he wants. So showing you an example of gas pressure next to a vacuum depends a lot on your definition of next to. If you mean a vacuum, like in a vacuum chamber next to the outside air, separated by a tiny sheet of acrylic, obviously
I guess.
Not. If next to means you have normal air pressure at sea level and then a very, very low air pressure at, whatever altitude, 37,000 meters, then yeah, I can show you that the pressure gradient exists, but our claim is not that they are separated by this much. They're separated by a huge amount because of the acceleration downwards. That's it.
Again, we can prove we can make objects float using electrostatics, right?
Yes, we'll get to your third question, maybe.
Okay, Roohif, you got a minute for your first question.
All right. Like I said, I'm going to talk about geometry a lot. So this is about measuring the 8 inches per mile squared. So you're on top of a mountain, has an elevation of 1,000 feet. You're looking across a valley to another mountain 30 miles away, which also has an elevation of 1,000 feet. If you measured the angle to that mountain with a theodolite, what would you expect that angle to be? If the Earth is a globe, please show your work.
Yeah, I predict it will be smaller, right? Because it's further away. I've never used the theodolite, so I can't show my work.
No, it's not about using a theodolite. It's about geometry.
Yeah,
What's the angle?
I don't know. I couldn't tell you the exact angle. Maybe you should show me and I can show you why it's just perspective.
Okay. I'm sure you'll just say it's perspective, but sure.
Of course it is. I showed you objects disappearing over a flat table.
Yes, and I gave you that.
No, you didn't. No, you didn't.
Well, okay, no.
My camera doesn't rise up as I zoom in, buddy.
Your lens extends, does it not?
Yeah, it doesn't.
Yes.
It doesn't go up.
If your camera is very, very slightly below the level of the table and it's very, very slightly angled up, how did you measure that?
It's not angled up. It's not angled. Why would it be angled up?
Because
I showed the camera.
That's what Mitchell did. We saw it.
The camera.
And you didn't go down.
The camera was straight.
Well, I'm not going to take your word for it.
It has a bubble level on it.
Yeah, I'm not going to take your word for it that it's perfectly flat.
So you think that I'm zooming in and the camera's going up?
As your lens extends, it goes higher. Yes.
Why would I angle the lens up like this?
Well, there's a question of whether you did that deliberately, or sorry, I'll talk about Mitchell instead of you.
Anyway,
yeah, whether Mitchell did that deliberately, unknown.
No.
Anyway, we're jumping around a little bit. We're on measuring drop due to curvature.
Yeah, due to perspective.
Well, okay. One of these scenarios, you will factor in 8 inches per mile squared drop. One of those scenarios you won't. All right, so you'll have an answer to compare to a measurement in reality, right? And if you factored in 8 inches per mile squared drop and it measures that way, that's a decent confirmation that there is 8 inches per mile squared of drop. Let's say you were on a mountain at 1,000 feet looking across at another mountain at 1,000 feet on a flat Earth. That angle should be 0, right?
No.
No.
The object, it gets smaller as it goes further away, doesn't it?
It does, but why does it drop below eye level?
Because it's smaller.
So in your starting video, you showed a row of streetlights, right?
Yeah.
Yep. And the top of the streetlights ramp down towards eye level.
Yeah.
What happens to the base of the streetlights?
Towards the horizon. They actually, at the end, look like they touch the horizon.
Right, but isn't the horizon at eye level? If your drawing's just streetlights in perspective view,
right?
The horizon's at eye level, right?
Well, it depends. Like, it's an optical location, but okay.
The vanishing point. Well, yeah, whatever.
Yeah, vanishing point. Yeah.
Okay, but the bases of those streetlights, they ramp up to the vanishing point.
The bases.
The base, like the ground.
Oh, yeah, I suppose so.
Yeah. Okay.
Right.
All right. So why does this mountain, which is at your eye level, fall below eye level when the base of the mountain ramps up to eye level?
Because it's smaller.
So the base, if the base of these streetlights ramps up to eye level, so the base is at eye level, and you're saying the top is now below eye level, you've got an upside down mountain. Do you see that?
No. Why would it be upside down?
Because you said the base ramps up to eye level. Yes.
Right.
Your base is at eye level. The base of the mountain.
It depends. Like the streetlights thing I gave you. I don't think that the camera is actually horizontal. It's looking up at the streetlights to see them.
That's
right.
That's okay.
Yeah. So if you're looking up
horizontal,
so it's like if you're looking at a star in the sky, right? That's not the horizon anymore, right?
Sure.
But it's very far away still, right?
Yes. How far away? Sorry.
So why wouldn't a mountain that's far away, 30 miles, get smaller due to perspective?
Yeah, the angular size does get smaller, right? But the top of it.
So why wouldn't you?
It's at your eye level.
Yeah.
Why does it drop? Why does that point drop?
Smaller. It's smaller.
Okay, we'll start again with your street lights. The top of the street lights ramp down to eye level, and the bottom ramps up to eye level.
Mm-hmm. You're on the mountain, right?
Yes.
Okay. If we were on top of the streetlights, then what would happen?
They would look perfectly straight. Yes, straight across. They wouldn't ramp down.
You'd look down. You're looking down. Yes, you would.
No, you don't.
If you're standing on top of a streetlight, you wouldn't look down to see the other streetlights.
If I'm at the same level as the streetlights, they will just be a straight line.
If you're standing on top, you're saying standing on top of a mountain, right?
Yeah.
Yeah. If we're standing on top of streetlights, looking down at other streetlights at the same level, would you be looking down?
Am I above the streetlights?
Yes.
Yes. Yes, I'd be looking down.
Well,
and they would be ramping up.
There's your answer.
Yeah, they'd be ramping up to eye level.
There's your answer.
All right, let's go on.
You're looking down. You're looking down.
I'm not sure that's an answer.
You're looking down.
Because
I'm above it.
Simple.
And it's ramping up.
Angel, go with your next question, number 2.
Yep.
So every 6 months, the day-night flip. I'm sure you looked at that.
Yep, I did.
Do you need me to explain it again, or should?
No. I've answered it.
All right.
So in your question, you say the Earth rotates once every 24 hours. That is technically incorrect. All right. The Earth rotates. Well, sorry. It takes 24 hours for the Earth to spin around and face the sun again.
How long, sir?
24 hours for the Earth to turn to face the same point of the sun again.
Right.
Right. That is not 360 degrees. Okay. So we are rotating and we are also in an orbit.
Orbiting. Yeah.
Yeah. So at 12 o'clock one day, right, we start spinning, blah, blah, blah. We're also moving around in an orbit. Okay. So when we have done a full 360 degrees, we're not actually pointing at the sun again. We have to rotate a little bit further to point back at the sun. I'll put this on a...
So you're saying this? So you're saying the Earth rotates more than to adjust for it, right?
Yeah, a solar day is about 361 degrees of rotation, and a sidereal day is 360 degrees.
Okay.
Right, so can you see on the screen?
Yeah.
How that makes sense?
So if the Earth is on an elliptical orbit, then you realize that the Earth would have to speed up and slow down, right?
Yep.
The Earth speeds up and slows down in your model.
Yes. It's called the equation of time. Yes, it happens. Yep.
Interesting.
Yeah.
Never heard of it.
Okay. Anyway, just
so
a sidereal day on the screen. Sidereal day is 23 hours, 56 minutes, and 4 seconds. That is exactly 360 degrees of rotation.
Right.
And then there's a couple of minutes.
So you're saying that it takes 23 hours and 56 minutes to rotate? Is that right?
360 degrees, yes.
Okay. The thing is, we don't set our clocks to 23 hours and 56 minutes.
Correct.
So why wouldn't night and day flip if we don't set our clocks to that?
Our clocks are 24 hours. That is the time it takes for us to point back at the sun again. All right, that's not 360 degrees.
23 minutes and 56, 23 hours, 56 minutes, or 24 hours is the time?
23 hours, 56. No, 24 hours is a solar day. So looking back at the sun, that's more than 360 degrees.
Right. So that means the Earth has to speed up and slow down, which we don't feel.
No, not relevant.
Well, it is.
No. The rotation doesn't slow down. You're talking about the orbital speed.
No. I'm talking about the rotation of the Earth would have to speed up and slow down. Yes, it would. You're in an elliptical orbit.
I just said we're talking about the rotation of the Earth, not the orbit. The orbit speeds up and slows down. The rotation doesn't.
The rotation would have to speed up and slow down.
Why?
Because to adjust for the elliptical orbit.
Oh, why?
Yes.
I don't understand why.
So hang on, in your mind, a solar day is 24 hours, right?
Yes.
A sidereal day, meaning how fast the stars spin, is 23 hours, 56 minutes.
Sure.
So that's what it is. That's why it's called sidereal, because stars, right?
Sure.
So like it still doesn't work out. How would like you're saying that the Earth rotates how much in degrees?
For a solar day?
For reality.
Well, they're both reality. There's different measurements. Like for it to rotate and point back to the sun is 24 hours. That's what we've defined it as.
Really?
That's 24 hours. Yeah. For it to rotate 360 degrees.
How much degrees is that?
About 361.
It's 361.
Yes.
So that's why that's why it should change speed. You realize that, right?
No, the orbit changes speed. The orbit changes speed. The Earth rotation does not.
Right. So how do we not feel this motion, that change, if we're actually moving in space?
Because we're on it and it's a free fall motion. That's one. And secondly, it would be incredibly tiny.
Yeah. Well.
Yeah. Well.
Okay, Roohif, your second question.
Oh, yeah. Good. What is my second question? Second question is, which mountain should be higher? If you have been in this debate for any sort of length of time, you would have seen the world record photograph. So you are standing on top of Pic de Fenestrelay, looking across to Grand Ferrand and Pic Gaspard. Which one should appear higher, assuming the Earth is flat?
Assuming the Earth is flat.
Show your work.
I think the second one should appear slightly higher.
Okay. I agree.
Yeah. Yeah.
Would you like to see my calculations?
Sure.
Yep. They're on the screen. So this is for a flat Earth. We've got Grand Ferrand is 68 meters shorter. So it's a very, very tiny angle below eye level and below horizontal. Pic Gaspard is 1,000 meters higher and 0.14 degrees higher. So yeah, I agree. On a flat Earth, it should appear higher. Have you seen the photo?
No.
Oh, okay.
Didn't even look at it.
Okay, cool. That is Grand Ferrand there.
Mm-hmm.
And that is Pic Gaspard. Grand Ferrand appears much higher than Pic Gaspard because the Earth is a globe.
Right. So you can put a math equation to a flat surface like my kitchen table, make into a sphere, right?
No, I can't do that. How do I do that? Please show me how to do that.
But I showed you objects disappearing over a flat table, bottom up.
Right. And I've explained why that is.
Your explanation is just nah. You get that, right?
I've given you an explanation. The camera is very slightly below.
No,
it's pointed upwards.
It's not pointed upwards.
You just said my explanations are nah. You literally just said no. Okay. All right.
Yes.
It's been demonstrated. I will dig that up for you after the debate.
Okay.
You can see my camera again anyway if you want to.
Yeah. 1 second.
Okay.
Oops.
Did he answer that? Yes, right? He gave you his answer.
Yeah.
Okay, Angel, your third question.
The horizon is an optical location. I think that was my question. So if you're...
Oops. Sorry.
So if you're at 120 feet in elevation, how far down do you expect to look? And then I'd like to show a video.
Cool. 1 second. Share screen. I had a visitor, so I had to kick him out. All right, sharing again.
Okay.
All right, so I made this in GeoGebra just for shits and giggles. You can set the observer height here, and you can play with how much refraction there is. This light radius of 45,000 kilometers equates to what we use as 7/6R in the curve calculator, and we get an angle down to the horizon of 5.67 degrees. That's my answer.
Cool. So is the horizon a geometrical location or optical?
I don't see those two words as mutually exclusive. I can do geometry on the horizon, right? It appears in an apparent position, so it's not in its actual position. Yep.
It never is, right?
Yeah, pretty much.
But it's also geometric in your world, right?
When you say geometric, do you mean
like a location?
Can I do geometry on it? Yes.
A location that's there that drops down.
Yes. It is a physical location, but due to refraction, it appears in an apparent position.
Due to refraction.
Yes.
So if we see 10 times further than the geometric location, is the Earth 10 times bigger?
Can you clarify what you mean by geometric? Do you mean unrefracted?
A physical location.
The refracted horizon is a physical location. What do you mean by geometric?
Geometric, the 8 inches per mile squared that you use. That's a physical. That's a physical location, right?
Yep.
If
so is the refracted horizon. Yep.
If it's a ball, it has a physical curvature to it.
Yep. The refracted horizon is also a physical location.
So your answer here is at 120,000 feet. This is this to scale, like this lines here?
My thing on the screen, yes. Yep.
Yeah. So you should be looking down at the horizon quite a few degrees,
Yes.
right?
Yep.
Cool. Can I share my screen now?
Yes. I'll have to stop sharing.
Let's see.
Oops.
And we'll go right to your last question here, Roohif, right after this video. There you go.
We're going 2,000 miles an hour!
Guys. Oh, wow. Okay, we're good. Loosen. Oh my gosh! Oh! Guys! We're floating!
Is that Dude Perfect guy?
Look at the sky! Oh, guys. All right, now take it in, guys. Look. See the curvature of the earth.
There it is. 70,000 feet.
So
It's the door stop, Felix.
you can see here, it's lifted to eye level, right?
Is it? How did you measure that?
Okay, I don't.
Well, look at it. Should you be able to see the horizon through that little capsule hole in your world?
5 degrees.
Or should you have to go out and see it?
5 degrees is not much.
I almost wait.
About 2 millimeters above the surface.
So in your world, the Earth has a geometric curvature that hides objects, right, at ground level.
When you say geometric, I assume you mean unrefracted.
Okay, call it that.
Unrefracted.
How high up do you need to be to actually see this curvature?
So you're talking left to right curvature or hidden obstruction curvature?
Does the ball only curve in one direction or all directions?
No, all directions, right? But are you talking about objects being obstructed bottom up or left to right curvature?
Left to right. Left to right.
So the higher the better. It depends a lot on field of view mainly and altitude. So you can see it from a plane.
If we send, we can see.
Well, we're getting away from the original question. So let's go ahead and have Roohif answer or ask his last one.
So what was my last one? Hold on.
I don't remember.
Third. My third question. I have to read this off. Hold on 1 second. My third question was about Canigou, and it was, you are standing on a hill north of Marseille in France at 333 meters, looking at Canigou, which is 2,785 meters and 265 kilometers away. Assuming a flat Earth, how much of Canigou do you predict is blocked by the horizon? And again, just for Benny Boy, show your work.
Almost all of it, if not all of it. But I'm assuming most of it. Yes.
Blocked?
Yep.
Did you show your work?
No. I don't need to show my work over a flat surface to make objects disappear.
Okay, can I just share a...
Can you do maths on my kitchen table and make it a sphere?
No, I can't.
But I made objects disappear bottom up on it.
Yeah, well, again, please model that.
You can say no all you want, but the camera doesn't rise up as I zoom in. You know that, right?
Well, where's my camera? Hang on. Oh, it's out of the camera.
Like it's on a stand that has a bubble level on it. The camera would not rise up.
And what's the sensitivity of that bubble level?
If anything, it will dip down because the camera's really heavy and it dips down.
Yeah, I will show you.
You know,
I'll dig out the video.
Have you held the P1000 before?
No, P900. I know they're heavy.
They're very heavy.
Super heavy. Yeah.
You zoom in as you hold it with no stand. You zoom in, and your hand will go like this. That's how heavy it is.
Yeah.
So if anything, my camera dipped down, and I could still see over my flat table.
I will dig out the video.
Let's go on to claims. And Angel, you should do a third perspective of that camera.
I did. I did. It was in the video. It was in the intro. And he still
maybe I didn't
denies
see
it.
it. I'll have to watch it again.
He still denies it.
Okay, let's go to claims. And I don't want to get stuck in any loops. So if I hear the same thing that we were talking about in the questions, I'll probably move us on.
Well,
just,
all three of his questions were the same question.
Well, what I mean is if we go back and forth again, if you bring up the camera and he says no, it wasn't level, and you say yes, it was, then I'm just going to move on because we've already determined that is the case. That you're saying it was level, he says it was not. So let's go with your first claim. You've got 2 minutes.
My first claim was the gas pressure thing. So you cannot show me a gas pressure next to a vacuum, coexisting next to a vacuum, without a solid barrier between them. Obviously, we could model this. We could build a vacuum chamber, put a barrier between, have air pressure in one, have a vacuum in another. So we can model that. But your argument is the Earth does this magically because gravity.
It's not magic.
How does it do it?
Right, we have a downward acceleration.
Is a downward acceleration due to gravity or due to electrostatics? Really?
I honestly don't care. Don't care. Yeah.
No, you have to care because
you don't get to dictate what my positions are. Right?
Okay, well, can I tell you that?
I don't care about Einsteinian gravity. I don't care.
Yeah. Well, you should. We can make objects float. We can make objects float with electrostatics.
Is that your second claim? Is that your first claim or second claim?
First. Can you demonstrate someone using gravity to make objects float?
Yes. Helium balloon.
Really?
Done. Done.
So buoyancy,
funny about that?
So buoyancy and density of electrostatics is now gravity.
Okay. As I asked before, what is the formula for buoyancy? Is there a little downward acceleration in there?
No, there's an upward.
No,
and it's A. It's A.
Yeah, that's fine.
A. Yeah.
That's fine.
Acceleration.
Whatever the acceleration is, there is a downward acceleration. That's all we have to agree on.
For buoyancy.
Yes. So do we agree there's a downward acceleration?
Buoyancy means, like, if I let go of a helium balloon, it's accelerating upwards, right?
Yes. Because?
Yeah, of electrostatics.
Because there is a downward acceleration. It's displacing.
Float. Yeah. We can make objects float with electrostatics. You can never do this with gravity.
Hang on. I thought that was your second claim.
No, let's go to your first claim, Angel. I mean, Roohif.
Yeah. His first claim was gas pressure without a container, not electrostatics. Like I said,
it's to do with that.
Oh, yeah.
Okay, Roohif,
I know, but they're not separate things. Can I actually answer that? His actual claim?
Oh, sure. I thought you were answering it.
Yeah. Well, so can you prove that things fall and float due to gravity and not electrostatics?
Well, we'll get to proof. Gravity? If you want to talk about proof, we can do that as well.
And I thought that's your third claim too. By the way, that's your third claim is about items dropping.
He's jumping.
Let's stick to the first one that you asked. Can you do a gas pressure without a container?
Yeah. All right. So he gave an example then of, let's have a little pressure, have a little vacuum chamber, and then open the container and the gas rushes out. Of course it does. No one denies that. Yeah, but it's a contained environment, and you got a vacuum inside and gas pressure outside. No one disagrees with that.
No. Well, yeah. Anyway,
okay. We have a demonstrable.
I'm not using the Earth.
Okay, but we do have a demonstrable pressure gradient in the atmosphere. It's 14.7 psi at the surface, and it just keeps getting lower as you go up.
Right. So why doesn't that fill the vacuum?
Because there's a downward acceleration.
Right. So if I have gases, right, in a container, and I'm on the surface of the Earth, and I open the container where gravity is the strongest, it will seek equilibrium with the rest of the Earth.
Will it?
So yes. So why doesn't that? So why, when gravity is weaker, why doesn't it just fill the vacuum?
Okay, you said it would seek equilibrium. We have a 14.7 psi pressure at the surface, and however small you want to accept, let's say it's half a psi at 120,000 feet. That hasn't equalized, has it?
Obviously, because it's contained.
Oh, what is the requirement for a container? What does it stop?
The pressure. It holds the pressure.
Stops it equalizing. Right?
Right.
What is, when this pressure gradient, is there a reason that that the pressure stops decreasing, or will it just decrease until it gets to effectively zero?
Probably not.
Like close to zero? Very close to zero?
Close to zero, maybe.
Yeah. Okay.
Not zero.
So if there's a barrier where the pressure is effectively zero, very close to zero, it does nothing. It's not required.
Yes, it is.
What's it doing? If there's no pressure up there, what is it doing?
If there's no container next to a vacuum, then the pressure will equalize with the vacuum.
There's no air up there. It's not doing it. It's not stopping any air particles.
Do you know how strong the vacuum is in space? It's huge. Yeah. We can recreate vacuum here. We can recreate a vacuum on Earth, and we need concrete walls like this, right? So yes, we do, to hold it, because it's so strong. And the one in space is claimed to be almost double that.
Yeah. Do you understand?
Why, if we don't have a physical barrier between air pressure, why would it not equalize?
Let's say this is going to be a little bit of a condescending physics lesson.
Why don't we lose all our atmosphere? Why don't we lose it?
Because we have a downward acceleration. If we have a vacuum chamber, right, a little Perspex vacuum chamber, and we get it down to 0.001 torr, whatever, right? Something very close to zero, but only 2 or 3 decimal places, right? We've got 14.7 psi on the out and very close to zero, but only about 3 decimal places on the inside. The pressure differential between the outside and the inside is 14.7.
Did you just say you needed a container to make a vacuum?
We've got a Perspex vacuum chamber. I didn't say we don't. Don't put words in my mouth.
So you need a container to make a vacuum.
On the surface of Earth, yes.
Oh,
Happy?
so but in magical space, no, right?
Space is not magic.
Oh, right.
Okay.
It just breaks laws of thermodynamics for no reason.
Incorrect. So on our little vacuum chamber on my desk, right, we've got 14.7 psi on the outside and very close to zero, let's say 2 or 3 decimal places, 1.
Inside the vacuum.
Yes, so very small.
Okay. Yeah.
The net force, the force that is trying to crush that vacuum chamber is 14.7 psi.
Right. On the outside?
Yeah. 5 millimeters of plexiglass, whatever it is, acrylic, right, can withstand that. Okay. Cool. If you then somehow get like a 10 to the minus 17 torr vacuum in that little vacuum chamber, how much force is on the outside? Really? What's the force?
The walls will go like this.
Right. But we said 0.001.
It'll implode.
0.001. There was 14.7 psi.
Do you know how strong do you know how much force that creates, right?
Yes.
Like internally, right? Is that what you're talking about?
No, not internally. Not internally. Externally. How much force is there externally?
It's still the same, right?
Right.
Externally.
So it's not going to crush.
Okay. So what part of that is not a container? Like you gave me an example of a contained vacuum.
Yep. Yes.
Right. So you think that space does that magically without
not magically, no.
Okay.
It's not magic.
So how can you have? Why wouldn't it equalize? If you open that,
because we have a downward acceleration. Acceleration.
Okay.
Let's go.
Let's open that container.
We beat that one.
That you have.
Yeah. We beat that horse. Let's go with your. Yes. That was Angel's claim. So this is your first claim.
First claim. Yep. What is my first claim? Fuck. Hold on.
Is that only my first?
Yeah. Where's my claims?
Took way too long for that.
Yes.
My
first claim is celestial navigation. Fantastic. I'll try and be fairly quick, actually. And I'll share
a minute. Hopefully.
Second.
So it should be a minute. And let's try and wait till he's done, Angel, and then we'll have him You need a little longer?
Oh, maybe. Celestial navigation is just the process of finding your position on Earth, given the angles to 3 different stars. There's a big book where people have tracked the stars for hundreds, if not thousands of years, and it's called the Nautical Almanac, and it will give you the coordinates on Earth at which the star will be directly overhead. That's called the geographical position, and the fundamental rule of celestial navigation is that if you back away from a star, any star, that star will drop by, if you back away 60 nautical miles, that star will drop by 1 degree of elevation. You've obviously heard that with Polaris. So if you go away 1,200 nautical miles from the North Pole, then Polaris will be at 70 degrees north. And yeah, that rule applies to all stars, and it is the fundamental principle of celestial navigation. And this rule does not work on a flat Earth. All right, so this is a little example. We're just trying to work out the height of this tree. So we set up a angle measuring device, measure the elevation angle to that tree, and then do some very simple trigonometry to work out the height. So the height equals the distance times the tangent of that angle. And this same, on a flat Earth, this same geometry should apply to celestial navigation. We should be able to look at a star, know how far away we are from it, take an elevation angle, and work out the height to the star. So in this case, we are 4,800 nautical miles away, and we measure an elevation angle of 15 degrees. We calculate a height for the star, 1,286 nautical miles. Now, if we put a second observer and move him 1,200 nautical miles closer, then according to that rule of 60 nautical miles per degree, the elevation angle has to go up by 20 degrees. And we know that we are now 3,600 nautical miles from the star. And that makes the height of the star 2,500. Uh-oh. So the star cannot be simultaneously 1,286 nautical miles and 2521 nautical miles. The geometry of celestial navigation doesn't work on a flat Earth. And you said you've been around for about a year. MC Toon has had an open challenge to flat Earthers for almost 2 years to show how celestial navigation is done on a flat Earth. The prize is 10 grand, and no flat Earther has come anywhere near close to completing the challenge. The end.
I'm sure they have, but he just ignores it like everything else.
Oh, please show it.
Angela,
I might not have it, but please.
Do you have a response to that or refutation?
Yeah, so celestial navigation, how the hell did, like, we have constellations, right? So in your model, how do we still have constellation if the stars are expanding at 4 times the speed of light?
No, stick to the answering the question.
Navigation.
So what was the question?
So his claim
doesn't work on a flat Earth?
His claim was celestial navigation.
Okay, so celestial navigation, the way he's doing it, depicts you on a flat hemisphere, half of a sphere, and then hijacks perspective and calls it Earth curvature. Why wouldn't a star that's at your zenith, right, be higher than a star that's further away from you? And why would a star not dip into the horizon?
It would on a flat Earth, but I think you missed the point of that little
how did
presentation.
So you determined star distances, is that what you're telling me?
On a flat Earth, I think you missed the point of that presentation, right? Yes, on a flat Earth, if you moved away from the star, it will drop, right? But the whole point of that presentation is that there is a linear relationship. If you back away 60 nautical miles, then it will drop by 1 degree, right? On a flat Earth, that relationship is not linear. It's a trig function.
Okay. But you're depicting yourself in the middle of the Earth.
No, I'm not.
Yeah, you are.
No, I'm not. I'm on the surface. How would I get to the middle of the Earth?
Can you bring up like a thing, I don't know, a demo of like how it works, both trig and with the sphere? Yeah.
Yes, I am not at the center of the Earth. I am on the surface.
Well, let's see the picture.
Yeah, hang on. Where is it? There it is.
So there's not going to be a line to the middle of the Earth?
Yes, there is. Yes, there is. But I am not there.
Wait a minute. What? Why is it?
What?
Why is it to the?
Are you at the center of the Earth? What? I'm at the center of the Earth. No,
Yeah,
I'm not.
Why is it depicting you from the center of the Earth?
I'm not here. I'm not here.
Right.
I'm here.
Okay. You're not
Okay.
there. Right. Yeah.
This is me.
Right.
Not at the center of the Earth.
So why is that to the center of the Earth? If we're only talking about the surface.
That defines the sector of the circle, right? So do you know how the process works, right? We're here.
Yeah.
We're looking at the star. We get an elevation angle of 30 degrees, which means our co-altitude angle is 60 degrees. Okay? Now, because the stars are far away, necessarily so, these two yellow lines are parallel.
Right.
Right? So these are parallel, which means this angle...
How far away are the stars?
Effectively infinite.
How do you know
that? They don't parallax.
How do you measure that? They don't deviate. They don't deviate.
They don't noticeably parallax. Yeah.
Oh, so they're fixed in the sky then. That's how we use. That's how we.
You seem to be trying to get. I can give you a fair bit of detail on this, right? Stars have proper motion. Stars have parallax by which we can measure the distance in the order of light years.
So now we can measure it, but it has to be light years.
Again, for the purposes of celestial navigation, the only object that we take into account the distance for is the moon.
Could you determine how far away Polaris is?
Me personally, I'll just take whatever the latest.
Let's go to the next claim.
We're getting very much off topic.
Yes, so it's your turn to claim, I believe. No, wait. Angel went first?
It's mine.
No, that was mine.
It's yours. Go ahead, Roof.
No, it's Angel's for his.
Oh, sorry, this is the second one?
Horizon.
Yeah, go ahead. Your second one, sorry.
Yeah, so my second, the horizon's an optical location. Changes day to day due to atmospheric conditions, and we can demonstrate objects disappearing bottom up over a flat surface. So you can put all the math equations you want to a flat surface and make it a sphere, but it's still a flat table.
Okay, we're banned on talking about that bit anyway.
Well, we've kind of gone over that. We can actually, I mean, you're just going to explain it again. Go ahead.
Yeah, so
unless you want me to go
the
to the
horizon, when you say the horizon is optical, do you mean it is not physical?
I mean that it changes.
Okay, I agree it changes. Yep.
Yeah. But it's also in your world geometric, right? Like it has to have physical curvature, right?
There are a whole bunch of words here that I'm trying to get a clear understanding of. You keep saying geometric.
So we can do a time lapse. We can do a time lapse of the horizon, see that it goes like this.
Let's stick to this part of the claim. His claim is the horizon is an optical location that changes day to day with weather and atmospheric conditions. I'm assuming you would agree with that first half.
Yeah, and the variation happens most if you are close to the surface.
Okay, so you agree it's optical. Okay.
Then the second part...
Again, these words, right? These words have unclear meanings.
So, like,
do you mean by optical,
where we see it,
not physical?
Where we see it is an optical location that changes.
You would agree with that?
It's an apparent location, right? But it still is a physical thing.
Yeah.
So then his next part of his claim, let's say you agree with the first half. The next part is objects can disappear bottom up due to perspective on a flat surface.
I'd love to see that modeled somehow with geometry.
I just did it.
With geometry.
I just did it over a flat table.
Yeah, model it with a camera. I'll show you what I mean.
Okay.
Hang on. I've got so many freaking slides for this. Hold on.
Like in your world, does the sun set? Do you understand how a sunsets work on a flat Earth, right?
No, I don't.
You don't know how that. No wonder you don't get it then.
I've heard people say how they think it does.
No wonder you don't get it then. No wonder.
Please again, show me the geometry. Like I said, my intro is 30 seconds.
Show how a sunset works on a flat Earth that people still don't understand.
No, I understand what you think it is.
Right.
It's nonsensical.
I understand
typical flat Earth is.
Streetlights converge into the horizon?
Yeah.
Okay. Why wouldn't the sun do that?
We can describe those streetlights with geometry and explain why that happens. We can't.
Why wouldn't the sun do that? Why not?
Okay. Does the sun shrink?
Yes.
No, it doesn't. I have measurements.
Even in your model, it does.
No.
Yes, it
Oh, you
does.
mean like by 0.5% or 2%?
Oh, so now it does change, right?
No, oh, Jesus Christ. Like I said, this is pathetic.
Don't bring Jesus
right?
into this, all right?
Yeah, but this is pathetic gotcha debating, right?
You just said that doesn't change, and now you're saying it changes.
During the day, over the course of the day, the sun
changes.
does not change angular size.
Yes, it does.
No,
Yes,
it doesn't. I have measurements. Do you
I
have
have
measurements?
proof. I have video proof.
All right, that's not part of this. We don't have that as a claim. So you now go to your second claim, Rufus.
Second claim. Bloody hell. Got to get track of my claims now.
And I'm trying to do it too.
Second claim is measuring drop due to curvature. So I did send Angel a video of mine where I took my theodolite around Sydney and took some elevation angles to a tower. I first measured the height of that tower and then made predictions for flat Earth and made predictions for the globe, and then compared those predictions to my measurement. And you'll see on screen here the first half of the table. Here's the actual measurement. Here are the predictions, and you'll see that the globe predictions are, about an order of magnitude or more closer to the actual measurement. So you can measure 8 inches per mile squared of drop.
Okay, that's his claim. Go ahead. You've got a minute if you got something to come back with that one.
Yeah, so I did my coin experiment, right? Let's say the coin over a flat table that I made disappear. Let's call it Mount Coin, right? You can't see it. I increase angular resolution to the coin, and now you can see the whole thing again. So now let's put that to the scale of the giant Earth, right? And call it, I'll put a math equation to it and say, oh, look, Mount Coin is...
I wish you would. I wish you would.
Oh, no, you should do it. Mount Coin is disappeared due to Earth curvature. But then I zoom in on a flat table and it's there again, completely.
Okay.
You see the whole thing.
This has nothing to do with obstruction.
Yes, it does. Could you see the coin?
We can see.
Could you see the coin before I zoomed in?
But no, this question is not about obstruction. This is a question about what angle, about measuring 8 inches per mile squared.
Yeah, and I'm telling you, I'm telling you, how do you measure it?
It's on screen.
Right. So by things disappearing, right?
No, this is not disappearing. This is an angle.
Cool.
We're talking about measuring drop.
So what's your point? Yeah, how do you measure?
Measuring drop.
You're measuring.
Yes.
You're measuring the 8 inches per mile squared.
Yes.
Oh, so my flat table, right, with the coin, you could put a math equation to that and call it a sphere, right? And say, oh, look, it's blocked by a sphere. Why not?
Again, this is not about obstruction, not about things being blocked bottom up. This is about measuring 8 inches per mile squared, not about obstruction.
Cool. Okay. So if we can see past the geometric horizon 10 times,
which would infer obstruction again. This question,
right, but anyway,
is about drop.
We can see past 8 inches per mile squared 10 by more than 9 times. Does that make the Earth 9 times bigger?
Right. If you are talking about the black swan,
or is it? Yeah, or is it an optical location that just changes and everything that proves flat Earth is a mirage?
The refracted horizon changes position, and especially when you are close to the surface, like BMLSB 69 was, it can change by a lot.
Right.
I agree. Right. So get above the surface.
What type of refraction was that?
Looming. Yes.
It lifted up.
Yes.
So what did it do? It lifted it up, or it moved the water down?
No, it lifts everything up.
Have you seen this before, Neil? I've seen an object like a boat looking like it's floating. I've seen that before. Have you seen it?
That's not looming.
Okay.
Yeah.
Okay, Angel, let's go with your third claim.
Hang on. Oh, sorry. Can we? Sorry, I just put this on the screen. When I said, if you're really close to the surface, refraction is incredibly variable, right? On screen, there are just 3 measurements. I've literally done hundreds of measurements on the horizon, all right? And you can see my prediction. No, this is the angle to the horizon. So this is not measuring drop now.
Okay.
Well, no. This is me making measurements from about 40 meters, 80 meters, 156 meters. I've done a stack quite close to the surface, and the results are all over the place, right? Because once you get close to the surface, refraction is highly variable, right? But once you get above the surface, preferably by 80 meters is good, then refraction is entirely predictable and very stable. And that's why my measurements match prediction near exactly. All right, but you got Black Swan. You got this guy. He went there, 90 days or something, or maybe 70 days out of 3 months. Took a whole bunch of videos on all those days, and one day he got the Black Swan.
Yeah.
Yeah. Get away from the surface.
Do you realize why it's called the Black Swan, right?
Yes.
Okay, Angel, make your third claim.
Objects fall and float due to relative density, depending on what medium they're in. We can make objects float using electrostatics, but no one will ever make objects float using gravity because it doesn't exist.
Okay. Hang on. So many slides here.
Okay, that's it. That's your entire claim. Got it?
Yeah.
All right. Okay. So we can make
prove objects fall and rise due to gravity.
No, this is your claim, right? So I'm
your claim. He's just addressing that. Go ahead.
Yeah. All right. So we can make objects float using electrostatics and not gravity. All right. So we're not using this one. Can you share me, Jared?
Yep.
Oh, hang on. Whoops. I probably should share myself.
It's a good start.
Yeah. Oops.
You're shared.
There we go. All right. So this formula, F equals like the Newton's gravity formula. We're not going to use that. All right. That one's wrong. Doesn't work. Correct?
Right.
Okay. This one. So this is Coulomb's law of electrostatics.
Yeah.
Was this used in the experiment that you saw?
Like when you drop an item and falls.
No. You said you levitated something with, or you saw someone levitate something with
Van de Graaff generator.
Okay, so the Van de Graaff generator, what charge does it have?
Positive.
Positive. Sure. Okay. So if you put another positive charge above it, what happens?
Positive. So it generates an electrostatic field.
Yep.
And then I think it flips the polarity. I'm not entirely sure how it works. But basically, you put objects on it and then they float up.
Yeah, but is that explainable with this electrostatic law?
I assume so. Yeah, I don't know the formula, but yes.
Okay.
Now, I mean, you laugh, but
yeah,
can you prove gravity? Can you prove the bending and warping of space-time?
You do want to talk about proof. Okay.
Yeah. Can you prove the bending and warping of space-time caused a helium balloon to float?
Okay. So a scientific theory is an explanation
for
something that happens in reality.
Can you explain why a helium balloon floats due to the Einsteinian gravity model?
The Einsteinian? Probably not. I don't understand it well enough.
Why not?
Yeah.
But like that's what causes objects to float, right? Gravity.
Sure, yeah. Like I said, I hold to Newtonian because that's all I need.
But Newtonian's not used anymore, superseded by Einsteinian.
Yes, it is.
Einsteinian, the current gravity model we use is not Newtonian anymore.
Newtonian is used in 99.9% of situations. You only
physics,
need
right? Physics, yeah. Physics. If Newton saw the apple fall, right, and land in a pond, would he have presumed gravity?
What was his explanation? He didn't have a good explanation of gravity. He described it.
Right. So if he saw the apple fall into a pond and the apple's floating because it's less dense than the water, would he have said, "Oh, look, gravity"?
I don't know.
Or would he have just said, "Oh, look, density and buoyancy"?
I don't know what he would have said.
Right.
Anyway, you want to
go to your next one?
Proof?
No, let's go to your next
one. He doesn't
claim.
want to talk about proof?
What?
He wants to talk about proof. He's like, prove this to me.
Yeah.
And I get asked that so often.
Well, we're in claims, so you can go to your next claim.
You want us to prove things?
I don't ask for proof.
Oh, okay.
All right, whose turn is it?
Yours, your third claim.
My third claim is flight routes. There's a third? No, it's a fourth claim, right?
Are you on your fourth one? All right.
Celestial navigation.
And then his fourth. So I don't know if we got off track. Yeah, it's your fourth. Go ahead.
Yeah. All right. Flight routes are excellent evidence for the globe. Obviously, I'm going to use, because he subscribes to the AE map, I'm going to compare these routes to the AE map. This is QF6364 from Sydney to Johannesburg. You'll see them take off from Sydney and go southwest over Melbourne. And then at the other side, they enter South Africa from the southeast. You can get one of these things, which is an ADS-B receiver, ADS-B antenna, and you can listen for the planes as they cross over the coast, so you can verify what direction they are coming from. We could in fact have someone in Melbourne, just like you. I can ship you one of these antennas, and you can listen for QF6364 coming over Melbourne. All right.
Cool.
So on the AE map, going from Sydney to Johannesburg, goes over China and Saudi Arabia.
No.
It would if that's the straightest.
It follows that red line because of jet streams. Yeah.
Right. So what about the other direction?
Yeah, I couldn't tell you, but it follows jet streams.
Okay. So the other direction, going into the wind the long way around?
It goes into in the center of the flat map, I'm pretty sure on the outside of the flat map, the jet streams go clockwise, and then on the inside they go counterclockwise.
West to east. So this one goes from west to east.
Right.
Goes that way.
Wait,
so
which way?
Usually quicker.
Which way does it? Where does the flight start from?
Here and here.
Right. Yeah. So the jet streams go clockwise on the outside.
Okay. Irrespective of what direction they go, right? On the return leg, they're going into the wind, taking the long way around.
No, they catch the jet streams on the inside.
What?
The jet streams.
I've just shown you where the route is. This is the route.
Right. Yeah. So, and what are you trying to prove here?
That this route makes no sense.
But they don't use that route. They catch the jet streams.
Right. But the jet streams go one way.
Yeah. And then on the other way, they catch the inside ones.
I've got the routes on this. The blue ones, I think, are Joburg to Sydney, and red ones are Sydney to Joburg.
I can't really tell with this because it's so zoomed in, but
okay, all right.
Plus,
but they go the same route regardless of which direction.
How do you know that?
You can. I'll buy you one of these. You can listen for this plane going over Melbourne.
Why couldn't they still go the same direction and still pick it up with that?
Say that again.
Why couldn't they use their path and still pick it up with that thing you showed me?
Why couldn't they go a completely different path? This is basically on site.
Like okay, so?
Well, if they're nowhere near you, then you're not going to pick it up.
Okay, but like, when do you pick it up? Like at the location, right?
Yeah, probably 150, maybe 200 k's away at best.
Wow. So in where the plane's landing,
where it crosses the land, yeah. But your route.
So
your route. Where do you think? Do you think it follows this route?
I'm pretty sure they catch jet streams on the outside. Yes.
I'm not sure you're picking up what I'm saying here. These are ingoing. These are both directions, right? These are both directions. They're going the same route in both directions. One of them must be into the wind. One of them must be with the wind.
Wait, say again. One of them must be not with wind. So
one of them, if they're following the same route, whether they're heading east or west, right? One of them must be with the wind. One of them must be into the wind. Why are they flying into the wind?
No.
I'm so lost.
They catch the jet streams on the outside. Then when they come back, they catch them on the inside towards the north. North.
Looking at, can you see the red and blue?
How do you know that? You're saying you confirm that by picking up the signal when they're landing.
Yeah, the direction that they're coming from. Yes.
Wow.
Okay.
So how does that prove the flight path?
Right, because it's data. To go on the FE route, you've got to go this ridiculous route. It doesn't go that direction. Why not?
How do you know?
Because we have the data, the flight data.
Okay, let's go
from Melbourne.
I'm telling you, it's going the red route.
All right,
the red route.
Yeah.
Then it's going into the wind. Why
So
would
even leave this. See this, what you got here?
Yeah.
No, it's following the wind. It's using a jet stream. Do you
then
see
the
how
other
red's-
direction is into the wind.
Do you see the red? Do you see the red?
Okay, let's
How
go to
it's-
your fourth.
How it's more south.
Hang on.
You see the red? How it's more south.
Oh. Yeah, but here, right?
Oh my god!
They're
The other
same.
one. The other. Go back to Australia.
Yeah.
You see? Yeah, this. Do you see how that red line there goes way south? Why does it go south?
So does this blue one. So does this blue one.
Okay.
Like, it's the same route. One way you have to be heading into the wind.
Look at those blue lines on top.
Yeah. Yep. And whoops, hang on. And look at those red and blue lines. They go the same route, regardless of which direction.
Okay, Angel, your fourth claim.
Yeah.
Let's move on.
Let's see. What is my claim? The Salynalan eclipse destroys the globe, gets hand waved away by refraction. You have to believe that the sun and moon are mirages caused by refraction, even though the eclipsing moon is starting. The eclipse is going bottom up when it should be top down. No, the eclipse starts from top down. It should be bottom up.
Okay, one sec. All right. So a Salynalan eclipse is seen when an observer is on the terminator line at the point of alignment between the sun and the earth and the moon due to refraction. You call it hand waving, but it's a fact. We have a density gradient in the atmosphere that bends light.
So does refraction work with shadows?
It's refraction. No, it's the absence of light. So the, sun, the moon is in shadow.
Why do we still see a shadow if it's not refracting shadows?
Are you talking about if you're standing on the moon and you see the sun?
Oh my God. If we're standing on the earth seeing an eclipsing moon, and that moon is actually not a real moon, according to you.
It's a real moon. It's a real moon. Yeah.
So it's not refraction now.
I didn't say it wasn't refraction. The refracted horizon is a real horizon.
If we see the sun and moon, the earth is not in between the sun and moon.
Yes, it is, because it's refracted.
What? How? Are we seeing the real moon?
We have an atmosphere, right? We have a density gradient.
Are we seeing the real moon?
Yes, the real moon in its refracted position. This is the same argument we had about the horizon.
No, not a refracted position.
Yes, in its refracted position, yes.
Is it a mirage?
It's not a mirage, it's in its refracted position.
Wow.
Mirages are distortions.
Wow.
Mirages are usually upside down.
Is the sun a mirage?
Not a mirage, it's in its refracted position.
Okay, so it's lifted up, right?
Yeah, it's loomed up, yes.
So you're not seeing do you understand the Salynalan eclipse? They claim you're not seeing the actual sun and moon, right?
Yeah, that happens every day. When the sun sets every day, when you are seeing the sunset.
No. I'm talking about the eclipse.
Yeah, same with the sunset every day.
So you're seeing a refracted mirage.
Not a mirage.
The sun. Yes, it is.
No,
it has to be in your model.
It's not a mirage.
In your model, it has to be. Otherwise, it debunks the globe.
It's not a mirage. Is a distortion, right? A distortion, like if you have an inferior mirage, you're seeing an upside down distortion of something.
Forget about which way the shadow goes, because that debunks it too.
We'll get there.
In your model, the Salynalan eclipse debunks the globe because you can see them both on the horizon. If they're both on the horizon, the Earth is not between them. So
they are lifted up half a degree.
Yeah. So half a degree. So how long does an eclipse take? 4 hours?
Something like that, yeah.
Right. You think it's 1 degree over 4 hours?
Well, I'm not sure what the time means there.
Right. Yeah, because it doesn't make sense. How would it be only 1 degree for 4 hours of an eclipse?
I'm looking that way to see a moon lifted up half a degree geometrically.
Yeah, it's a mirage in your model. It's a mirage. Yes,
mirages are distortions. This is not a distortion. This is just looming.
It's not between the Earth and Moon if you're saying it's not a mirage.
I don't know where to go from here.
Okay, we're good. We're good on that.
Why? Hang on. Like this, so you just hand waved it then. Like I said,
no,
right?
Refraction is a thing. Right.
Yes, you have.
Do we have a density gradient in our atmosphere?
Yes.
Does light bend through a density gradient?
Does light refract shadows?
No. Light's light.
But we see an eclipsing moon, right?
Yeah, it's in shadow.
Oh, but it doesn't refract. We should just see a moon, right? We should just see a moon phasing with no shadow. It should be see-through if it's only light.
I mean, see-through.
Do you get it?
I don't get a see-through moon, no.
We should see a moon, right? A moon eclipsing, right? Going red and then eclipsing the other way without a shadow. It should have no shadow because shadows don't refract.
It is in shadow. We see a shadowed moon because the Earth is in the way.
Oh my God!
All right, we're good. Let's go to conclusions.
No. Hang on.
Well, you have something else?
Hang on. The upside down eclipse.
Give him some time to recoup.
Oh, okay, champ.
Recoup.
Fuck me.
Huh?
I said recoup. Roohif, let's go.
Yes. All right. So the upside down eclipse. All right. I'm just going to give you a minute to look at this. Okay. You are this guy here. All right.
Okay. Sorry.
Okay. He's on the equator.
Yeah.
He's on the equator. The moon is going that direction into the shadow of the Earth. Okay. What does this guy see? What does he see, this guy?
He sees an eclipsing moon that
from which direction?
Is a mirage.
No. Don't worry about refraction now. Just look at it. What does he see?
Yeah, okay. What about if you're on top of the globe?
No. What does this guy see? He's looking at this. Turn him upside down.
Yeah.
Do I need to turn this upside down?
Right.
Is that better? What does he see?
Okay. Right. Yeah. He sees an eclipsing moon.
Where's the shadow? Where is the shadow coming from?
Yeah. It's becoming because the sun is casting a shadow in your world.
Where's the shadow coming? Where's the shadow on the moon?
From the Earth.
Okay. Can I have 10 minutes, please, Chuck? 10 minutes. I've got a annoying teenager.
That's right.
All right.
So in your world, right?
No. This diagram, what is he seeing?
Yeah,
where is the shadow?
He's seeing a shadow.
On the
moon.
Top?
Right.
He's seeing a top shadow.
Yeah. Okay.
What happens as the moon goes further into the shadow?
It eclipses more.
Yeah, from the top down.
In your world.
Do you understand the top-down shadow?
Yes, I get it.
Okay.
I get it. I get it. But it doesn't explain it because the sun and moon in your world have to be mirages. What do you understand about that?
It's not a mirage. Not a mirage.
Yes,
they are refracted. They are not mirages.
Can you see the sun and moon at the same time during the Celestial eclipse?
Yes.
Oh, so how come the shadow is seen on this?
Right, because the moon is in shadow.
All right, let's go to conclusions. We've got. We're just going to do 2-minute conclusions each. You go first, Angel.
Is it? Yes, sorry.
Yeah. So,
and everybody, if you want to have any questions for them, and we don't have much time with Roohif, but if you get them into the super chats, we'll ask right after the conclusions.
I could go camera off.
Okay,
camera off, and I can get going.
Yeah, we'll see how that goes. Go ahead. Start, Angel. Roohif, stay muted.
My conclusion is a flat table is still a flat table. Doesn't matter how much math you use on it. He hand waved my example of things disappearing over a flat surface, even though it clearly shows that it can be demonstrated easily. I haven't put the boat there. I put the sun there rising up, and then it goes down again as you zoom back out. I mean, if a sun is truly 93 million miles away, it shouldn't zoom up like that. It shouldn't move. I mean, it's really far away. He claims celestial navigation only works on the globe because they hijack perspective and call it Earth curvature. Hand waved away my Saturnalia eclipse, and just the usual stuff. That's it.
Okay, thank you very much. And
I will say the usual stuff as well. Like my intro is 30 seconds for a reason. Flurfs can't do geometry. I showed them how to measure the drop. I asked for a prediction for how much of Canagoo is hidden. In fact, can I just screen share something at the end?
You got 2 minutes, yeah? Or you got minute 45?
1 sec. The thing is, with Globers, we're not afraid to make predictions. So for Canagoo, here is... Well, I'm sharing now. Yep.
You're on.
Yep. Here is what it should look like on a globe on the left. So, you'd predict a fair amount of the mountain to be hidden by the horizon. Not a flat Earth. You can see all of it. And guess what the photo looks like? It looks exactly like the globe prediction. So it kind of comes down to a really basic thought process from Flurfs that they seem unwilling to make any sort of prediction or do any sort of modeling to say, this is what I expect if the Earth is flat, and this is what I expect if the Earth is a globe. The ones that do tend to have absolutely no idea about how to model things with geometry, or have terrible understanding of physics. Yeah, that's pretty much it.
Okay, thank you guys very much. Let's get to the questions if there is any. Let me check here. And we've got, and you can tell everybody first, go ahead, Angel, where people can find you. I know that you've got a TikTok. Right?
Yeah, I'm just on TikTok, Lights for Angels. Interesting channel I made.
I'll come and heckle you there. Lights of Angels. I can heckle you on Telegram, actually.
Okay.
Yeah, that'd be better.
Start there. And Roohif, where can people find you?
Roohif on YouTube. I don't make too many videos. I'm kind of getting a little bit bored with Flat Earth and heading back into genetics. Yeah.
Genetics.
So don't subscribe. Yeah.
Do you think we came from amoebas?
I think we share a common ancestor, yes.
Okay, let's go through. We've got Matthew D. Gregorio. Thank you very much. He gifted 5 memberships early on. Thank you. So kind of you. We've got Regina Gilby. Had 1 month of the Jeranism Club. We've got Cottonmouth Hero 8. Joined the Jeranism Club. We've got, I don't know what it is. I'm the ... He says 6 months member. I'm so happy. 6-7 years, and he still thinks he's on a spinning water ball. Guess that's talking to you, Roohif. We've got Matthew D. Gregorio, again, gifted 5 memberships. Very kind of him. We've got NPE, who's been a member for 15 months. Greetings all. Thanks, Jeranism. Love the debates. Now we've got a question for Angel, I'm assuming. Did I spell Angle? No, I don't think so. Did I? A question for Angel. Do you understand everything you see as a parent? From Kango44.
Yes.
Okay, thank you for that.
Cool.
We've got Kango44 again. He says, question for Angel. Put your camera above the table so the whole lens is, say, 1 centimeter above and make an object disappear bottom up.
Yeah, that's why I put the boat on the top to show that a boat disappears bottom up too. That's why I put it there. Is my camera below the water? No.
Okay. We've got Taking Back Eden says, Roohif, do you go against your God-given senses? Can you feel the Earth tilt of 23.5 degrees? Velocity change when you travel, hear, see the spin, or is it nonsense?
That's what I said when Flurfs have absolutely shit-house understanding of basic physics.
Yeah.
No, I don't feel the Earth spin.
The Earth rotates and changes velocity, but you don't feel that.
Right. Would you like a vector diagram of that?
Nah, I don't want your cartoons.
Of course you don't.
That's right, I don't want your cartoons.
Kango44 again says, question for Angle, why don't the oceans rush to fill the lower pressure system of the sky? If your answer is density, then isn't the air denser than the vacuum of space? Huh? Why don't the oceans...
The water... Why don't the water is more dense than the air, so it stays down.
Pressure? If your answer is density, then isn't the air denser than the vacuum of space?
Yeah, you can't have a vacuum or a gradient without a container in the first place. So
I'm not sure I understand the question, or I would ask it in a different way, but I don't.
I know that's really dumb. Really.
Okay, Roohif, has the gravity ever been measured as a force? From LJ. Thank you very much, LJ.
As a force. Oh, that's kind of a question of how do you view classical physics? Like there are forces in classical physics. In Einsteinian, it's not a force.
Yeah.
Okay.
They're superseded Newtonian.
Cool. Yep.
Taking Back Eden says Roohif admits his belief is nonsensical.
What?
Don't know what that's getting at either. Maybe it was at a certain point in the show that I would remember if I look back. Roohif, what is roughly the maximum distance you should be able to see? Do you think that with a powerful telescope and enough terrestrial refraction, you could see the back of your own head? Thank you very much. Thank you, RM.
According to math, you could.
So according to math, you can. Yeah. So there is a gradient that exists, and the black swan is an example of that, where the light is bending at the same rate as the curvature of the Earth. Obviously, you'll run into attenuation and resolution problems, but theoretically, yes, that gradient does exist.
Okay. We've got Taking Back Eden says, take the L, Roohif, or it's you versus Bible. Much love.
Oh,
he would debate that. He would debate that.
I probably would.
So Taking Back Eden, come to t.me/debatism and challenge Roohif on that.
You debate the Bible? So
not for the last 15 years, but yeah, it caused some marriage issues at the start, so I stopped.
All right. Well, I mean, you have a common ancestor with an amoeba and a strawberry, so.
Yeah.
Okay. Taking Back Eden again. Is Roohif Agent Smith from The Matrix? Much love.
Yes.
Taking Back Eden again. Is Roohif Mr. Anderson from The Matrix? Much love.
He's an Aussie, Mr. Anderson. That was his name. Hugo Weaving.
Leo Crow.
Australian.
$5 is Roohif. Do you have any proof nuclear fusion is actually happening on the sun?
I have no idea. I mean, it's explainable. Like I said, the word proof has a lot of.
Do you know how far away the sun is?
I do.
How far away is it?
150 million kilometers.
How is that determined?
Bouncing radar off Venus and drawing a big triangle.
So if you did the same thing to the moon, could the moon also be 93 million miles away?
No.
Oh.
You can parallax the moon. In fact, Jaren, let's parallax the moon.
I plan on it, yeah.
Yeah.
Do we have to be on the same longitude for that?
No, but it's nice. It makes it easier if it's kind of just in the middle of us.
Oh, I forgot one really good point. I just realized. But anyway.
Oh, go, yeah. My daughter's here, just being quiet, so that's good.
She's a good teenager. Come on.
Do you know about Polaris and the Southern Cross being visible at the same time?
Yeah, that's fine. Polaris is only the Southern Cross is only like 63 degrees south, something like that.
Hang on, from the Tropic of Capricorn.
From the Polaris from the Tropic of Capricorn, no.
Yeah.
No.
Well, it happened.
Okay. Please provide evidence for that.
Well, it was from 1862 Times newspaper. Captain Wilkins saw them at the same time at midnight.
Okay, that's words on a page. I would like to see that somehow repeated, or a photo or something.
I don't know if it can be repeated now with all the light pollution.
Oh, look, you talked about northern star rotations, all right? I've done northern star rotations. You can do it. We can see the northern stars. Right. So when you do a northern star rotation, you get partial circles, right?
Can we see Polaris?
Where is the center of those? Where is the implied center of those circles?
The implied center of those circles. All the stars rotate relative to each other, fixed, right?
Okay, but if you do a southern star trail, right? They rotate around a center point in the sky. For you, it's like 38 degrees up. Yeah.
Not if you face north.
Right, but we're doing southern star trails.
Right.
Yeah. So that center point of rotation is 38 degrees up elevation. If you do a northern star trail, the implied center of those circles is going to be like 38 degrees into the ground.
So you look more up, right? North?
Down.
Polaris?
To see Polaris, you're looking through the Earth.
Oh, you're talking from the south. Yeah.
If I take a star trail right from here of the north, yes, they go anti-clockwise. Yes, they go anti-clockwise. But if you were to plot the center of that circle, it's in the ground.
Yeah, because of perspective. Right. Very simple.
Okay, we have two more.
Very simple.
Two more comments here. Charlie says,
I can't believe you don't know how a sunset works.
Cheers, Jaron. What happened to the yes associated with Buy Me a Coffee appears not to be working. Oh, it's only not working during this show because I don't, donation interruptions would not be good for a debate. But thank you very much. And those will be turned on Thursday and Friday. There is no container stopping. Oh, this is from Kango44. Thank you very much. Again, very kind of you to support so much. There's no container stopping the water rushing to fill the sky, even though there is a big pressure difference. Just like there is no container stopping the air rushing to fill the vacuum. Gravity.
Oh my gosh.
Okay.
Is that a real question?
I think he's making a point more than a question. Can I ask both you guys to do something? If you both were to watch a sunset, and it could be from wherever you're at, over the course of the next, say, week or two, and you were to start a stopwatch when the sun disappears below the horizon, or you can even start a video camera if you want right when it hits the horizon, but let's say it disappears, you start your stopwatch, and you stop it when you can see no more light from the sun. right? So you're basically measuring the amount of time that you can see light after the sun sets. And if you did that today, and then you did it again in 3 months, what would you expect, Roohif, to be the outcome of that? Would the time that you're seeing after the sunlight be going up or down as we go from January to, say, March, April?
We've talked about this, didn't we?
I don't know, I'm asking you to do
Can I
that.
share my
We
screen
talked
for
about
this
it
too after?
as in what objective measurement are we making? Like, are we sticking a light meter out, or what are we doing?
No, I just think your eyes, telling me what your eyes show.
Yeah, I think that's a shit.
So it's better just to do math and not care about observations.
No, measurement. It's better to do a measurement than just guess and eyeball it.
Oh, so the measurement would be, if you take it on camera, wouldn't you be able to tell when there's no more light residual from the sun?
What's the threshold?
0 light.
It never is never 0 light here.
So it's always.
Can I share my screen just after that?
Yeah. So it's funny. I keep saying this to people when people don't want to do the observation. They don't want to do it for some reason. It's kind of weird to me.
Yeah, Jared,
we want some objective measurement.
So okay, hold on. Let me ask Ruhif, what would you prefer? Like a light meter, like a lumen meter?
Something like that. But then it might be cloudy. It might be something else.
Right. And that's why it's not I'm not just telling you do it on this date and this date. It's more of get an idea for what that number is today versus in 3 months. Because they'll be kind of vastly different. Vastly meaning 10 to 20 minutes different, but something you can easily discern with your eye. So I'm just wondering if it would be weird if you guys got the number as we head towards June as increasing, because you're in the south and therefore you're going towards winter, you should be decreasing, right? But we are in the north. Ours right now, if we did it in January and did it again in March, April, May, it's going to be increasing. So that would be weird if we're increasing and you're increasing. That's all I'm saying.
Yeah, I don't know. I think there are more determinative ways to measure the Earth. Yeah.
Yeah.
Sure.
Like using math, making a flat plane into a sphere.
Oh, please show how it's done. Please show how it's done.
Yes, go ahead.
Well, Eratosthenes did it.
No, he didn't. If you have three observers breaks the two flat Earth ones.
You didn't see my intro? You didn't see my intro?
Yes. Did you do any measurements in that intro?
Wait, are you saying you can't have 3 shadows that are a flat plane?
You know how I did the measurements to the tree, right? The shadow is a similar idea, right? The shadow from the top of that tree down to the ground. You could measure that and get the same angle. If you had 3 observers for Eratosthenes, you would, again, use trigonometry to pinpoint the sun. It won't work on a globe.
Oh, so
3 observers.
So if you did the same thing with the moon, would the moon also be 93 million miles away?
No, the moon is about... The moon does actually have parallax.
Yeah, but it appears to be the same size, right?
The angular size, yes, yeah, roughly.
Oh, so it could also be using trigonometry then.
No, we don't use trigonometry to measure the distance to the moon. We don't.
Do you understand that over a flat table you can make... actually, can I share my screen?
Yeah, we don't use trigonometry to measure the distance to the moon or the sun.
Thank you so much, Charlie. From the chat, folks, and the folks watching this gig, stay safe, friends. Thank you very much, Charlie. It's awesome. $50. Much appreciated. What are you showing? Are you I don't see a screen share.
I'll just screen share. This first off the sun. So I've got anti-crepuscular rays and crepuscular rays. Can you tell me how a sun 93 million miles away does that? This is a photo I took.
You have thrown the word perspective at me multiple times. I'm going to bring up
because you still
Google
don't get
Earth.
it.
I'm going to bring up Google Earth. 1 second.
You're going to bring up a cartoon. Yeah.
Well, I will show you how parallel rays give you crepuscular rays.
No. Can you tell me how the sun appears to be right in the clouds?
It's not. Those lines are parallel.
Right. Yeah.
All right.
It's like a train track. I get you. Also with what was my other thing? The Eratosthenes thing, right?
Yeah. 1 second. Crap. Hang on.
So do you see how over a flat plane with a local light source you could account for all 3 shadows?
No, you cannot. No,
really?
You cannot.
Do you see the image on the screen?
Hang on 1 sec.
Well, he's asking, can you account for the shadows?
Yeah. You can do math on this and say it's a sphere, right?
Oh, there we go. Oh, fuck, hang on. I'm trying to get to screen. There we go. No, measure them.
Dude.
Measure the shadows.
Dude, regardless of measuring, you could do.
You don't give a shit about measurement, do you?
Wait, I'm confused. What you're saying here,
change
Roof.
reality.
Help me out with this one. So you're saying, I don't know what you're saying here, Roof. You're saying that with a third shadow, and then you're saying measure it. So then that would require us to. Now we're saying that we're using that to measure the distance to the sun, right? But you guys on your model can do the same thing. You would not get the distance to the sun.
We would not get the distance because that's not how the distance is measured.
Okay, that's what he's saying the same thing.
No. He's saying 3 observers in Eratosthenes works on a flat Earth.
Yeah,
not for measuring the sun.
No, not for measuring the sun. For measuring the circumference of the Earth.
No. If you measured those shadows,
is my flat table a sphere now?
No. If you measured those angles for those 3 shadows on a flat Earth, they will meet at one point. On a globe, they will not. All right?
They will meet at one point.
Do it in reality.
This is my flat table, kitchen table.
I understand.
So any amount of math,
I see what you're saying. Then okay, I got you.
Any amount of math you do will not change this flat table into a sphere.
Right. Right. If you do this in reality with 3 observers and you assume a flat Earth, no, it doesn't.
Yes, it does.
Okay, let me finish the point
with
first.
With a local light source, it does.
You're saying it does work out, Angel.
It does.
What do you mean? It works as far as what?
I'm saying, right, that the Eratosthenes experiment, like it works on my flat kitchen table here with a local light source.
Right.
What if the sun was a lot closer and smaller? Why would that not work on a flat plane?
Right. If you do this in reality, okay, so not on your kitchen table, do it in reality. You measure 3 angles, right? Then you do some geometry and extend those lines, right? Extend those 3 lines. They will not meet at a single point. I'm seriously going to bust out the crayons in a second.
No, that is the truth about the lines where the lines would line up. Correct. They would not show the location of the sun, is what you're saying.
Right.
I get you. I'm not talking about the sun. I'm talking about the circumference of the Earth.
Right.
Yeah.
Yeah. If you have 3, using 3 observers for an Eratosthenes type measurement.
Yeah.
Does not work on flat Earth. They will point to different locations.
And does it work on a sphere?
What?
Yes.
3 observers.
Yes.
It works both the same on a globe that has a faraway sun.
Bring up your screen again.
It works on a globe. All right.
Roohif, if we had somebody at, say, I don't know what the degree would be, 45 degrees north, right?
Yep.
So how far are they from the equator?
45 times 60, what, 2,700, something like that.
Okay, and then if we had a sun above the equator, right, and we have somebody else who's on the equator looking at the sun that's past them, wouldn't we get a distance of the sun of 3959?
Sorry, on a flat Earth?
On a globe Earth.
No, you'll have is parallel views of parallel lines to the sun, or near enough parallel.
If somebody's at 45 degrees and somebody else is on the equator?
Yep. The guy at 45 degrees will see the sun at 45 degrees elevation.
Correct.
And the guy at the equator will see it overhead.
Okay.
Yeah.
Yeah.
So couldn't we draw a triangle?
If you're on a flat Earth, I was
asking about a globe.
Yeah.
How does that not work
on a globe? Hang on. I've been asked 2 questions.
Sorry.
On a globe, those 2 lines are parallel. They meet effectively at infinity. If we had enough measuring accuracy,
45 degrees and 90 degrees?
Sun's directly overhead, yeah.
Yeah, so you're saying that line is 90 degrees up, and then the guy from 45 degrees looking at an angle is also parallel to 90?
Yeah, those 2 sight lines are parallel. He's at 45 degrees latitude, looking south.
Okay.
Yeah, sees the sun at 45 degrees above the horizon.
Correct.
And the guy at the equator sees the sun directly overhead. Those 2 lines, the 2 lines to the sun, are parallel.
I'm so lost.
Me too.
That's
he's trying to
wait. If somebody's at the 45 degrees looking at a 45 degree angle at the sun, and then somebody's underneath it looking straight up, how are those 2 lines parallel?
Yeah.
Oh, you're saying I get you. I get what you're saying. I get what you're saying. You're saying on a okay, got you.
Is he saying like a faraway infinite sun with parallel rays?
He's saying like the soundly thing where they bend the Earth this way and they show that even though it's an angled line on a curved Earth.
So Roohif, if you understand that works, the shadows work on a globe. Sorry,
no, they do
Earth,
not.
Right?
Measure them in reality, and then tell me where the sun is.
They were measured in reality.
Okay,
why does it matter where the sun is?
Oh man, if you go into reality and measure 3 angles to the sun, right? I agree that two angles, right? You can get 2 angles on a flat Earth to point to a single point where the sun is, right?
So
2
like
angles
this kitchen
works.
table, right? Like the
2 of them
table,
works. Yep.
So what you see a third shadow, right?
I see the third shadow. In reality, that shadow will not be that length.
Okay.
In reality, that shadow will be a different length, that third shadow.
In the Eratosthenes experiment, they were different lengths.
Oh, fuck. Eratosthenes did 2. Can we agree?
He did 3. Didn't he do 3? See, this is why it's not story.
Yeah. Let's assume he did 2, right?
Right.
On a flat Earth, I can get 2 sight lines to meet at a point, and on a flat Earth, that's where the sun would be. Okay?
Well,
as soon as you add a third angle, they no longer meet at one point.
This is what what's his name said.
Whoever it was is right.
Yeah, Neil deGrasse Tyson.
Yes, as soon as you add a third observer, those angles will not meet at a point.
So I'll just share my
And
screen
they only
and I'll
meet
show
at a
exactly.
point on a globe if you bend the Earth. That's what he's saying.
Yes, yeah. And the sun's far away, yes.
I'll show you.
Let me look one more time, see if they're anywhere. I'll be good. I don't want to go too long. I did say 90 minutes. We are at almost 120. But I thought it was a good conversation. All right, that looks like all of them. Thank you guys so much for the super chats. Any final words from you guys? And we will head out. I'll be back Thursday. We're going to do a return episode of the Speaker's Corner. So get ready for that. That'll be at 3 p.m. Pacific. Get a lot of people a chance. And then we'll talk about how we'll do that going forward, which I think I'm going to do it monthly on a specific day at a specific time, so we get everybody to want to be there, want to speak on that day, and then we'll keep a time clock and keep it going, keep it moving, rather than do it every week and getting the same people every single week. So that'll be we'll have a return episode Thursday, and then Friday the Jeranism show will be at 3 p.m. Pacific also. Final words from you, Roohif. Thank you for joining me, by the way.
Thank you, Jaron. Always keen for this. Yeah.
Oops.
Look, come on, Caleb. Where's Caleb? Bring Caleb on. That'd be fun.
Caleb, Roohif challenging you. That's a call out.
Yep.
And Angel, thank you for joining us. Any final words for you?
Yeah, math doesn't change reality. My kitchen table is still a flat table.
All right. Sounds good. Thank you guys so much for joining us. Do your own research.